السلام عليكم دكتور. Do you hear me? السلام عليكم. Waalaikumsalam.
Okay. Welcome to this session titled Artificial Intelligence. We have four exciting presentation. Each presentation was last 15 minutes and followed by 5-minute two discussions. We can start by first one, paper number 104. Hi. Okay. Dr. MD Ismail. Dr. Ismail Hussein. Dr. توفيق زهران. Okay.
Yeah. Thank you. Assalamu alaikum.
عليكم السلام. You can start, Dr. Ismail. Paper number 104. Okay. Are you ready, Dr. Ismail? Paper number 104, ready? Yes, okay. You can start. Dr. Riyad, you can start. You can start now. Doctor. Dr. Riyad. Time. Do you hear me?
Hello. Hello, Professor. Can you hear me? Hello. Can you hear me? Okay. I can hear you. I can hear you. Yeah. Sorry. Um, I can share my presentation. Hello, everyone. Assalamu alaikum. it is a great pleasure and excitement that I stand
Uh,
before
doc-
you.
Doctor, your presentation disappeared.
Can you hear me, Professor? Yes.
Your presentation disappeared.
I'm also share my, yeah. Now available? Can you
No,
see my screen?
you can share your presentation, doctor.
Yeah, I already shared my. Can you hear me now? Right now? Can you share? Can you see my screen, Professor? Can you see?
No,
I'm already shared, but
yes, you can start, doctor.
yeah,
Can you share, doctor?
yeah, I'm
Share your presentation.
yes, share my presentation. Can you see my slide?
No,
We can see the slide online. We can see it.
But Professor cannot maybe see my slide, I think. Yeah,
Can you stop the sharing and start sharing again, Doctor?
yeah, sure. Um, yeah, I'm sharing my presentation. Can you see?
Sure, sure. Can
Can
you
you
share
see?
it again? Yeah, we can see now.
Can you see?
Yeah, we can see now.
Okay, thank you, thank you, thank you. Thank you, everyone. It is a great pleasure and excitement that I stand before you today to present our research paper title prediction and the lifespan of lithium-ion batteries, integrating initial data with machine learning approach. My name is Torifat Jamanria, and I am from Bangladesh. I'm honored to share my finding with you. Here is the outline of the presentation. I am going to brief this in the upcoming slide. Here is the introduction. Lithium-ion battery is a modern application essential for electric vehicle, renewable energy grids, portable electronics, and industrial system known for high energy density, long life, long cycle life, and efficiency. Battery degradation and prediction cycle life. Degradation is influenced by factors like charging rate, discharge cycle, temperature, fluid, and load condition. Prediction ramming cycle life is crucial for optimizing performance, safety, and maintenance cost. Challenge in battery life prediction. Significant variability in battery performance, even among similar manufacturing conditions. Traditional physics-based models are limited due to their inability to generate across different battery chemistries and uses proper. A role of machine learning in battery prediction. ML technique like this linear regression, CNS, LSTMS offer promising alternative to traditional models. Data-driven method enable accurate prediction with reduced computational demand. Here is the research contribution. A machine learning based framework is developed to accurately predict the remaining cycle of lithium ion battery, combined advanced feature extent technique with a linear regression model using elastic net regularization for high prediction accuracy and interpretability, support early assessment of battery performance, enable proactive maintenance and reducing its risks, enhance the ability to validate manufacturing process quickly, addressing variability in battery performance under different conditions. Lithium ion battery. A lithium ion battery dynamic equivalent circuit model is an essential tool for simulating the battery electrical behavior and optimize performance across a wide range of applications by incorporating parameters like an open voltage series resistor and a parallel RP. The model enables accurate prediction of battery behavior under both dynamic and safety state condition using these three equations. We can use the three equation. We can see that. Machine learning algorithm and net regularization linear regression model was used to forecast a cell remaining life cycle. This method is advanced due to the low computational demand and high interpretability, making it practical for examining the connecting between predictor and the target variable. Elastic net regularization was applied to address multi-connectivity and improve the robustness of the model. Here is the data set. Feature extension is essential for prediction the remaining cycle life of lithium-ion batteries, especially when utilized linear regression model by selecting and transforming raw data into relevant feature. The performance and interpretability of the prediction model are significantly improved. We can see figure 4 show. Sorry. The data set used in the study constant of measurement from 124 lithium ion cell, each with a nominal capacity of 1.1 ampere and a voltage 3.3 volt include described data barcode like cycle life and charging policy. Summary data for each cycle like discharge capacity, internal resistance, charge duration, and time series data like temperature, discharge capacity, voltage. These different data sets support the training and evaluation of machine learning model focusing on feature crucial for prediction battery regression and cycle life performance throughout every charge and discharge cycle. In figure, we can see figure 3 show the number of battery cells cells for training, validation, and test. The training data constant measurement from 41 cells, the validation data constant measurement from 43 cells, and test data content measurement from 40 cells. Here is the feature extension. Feature extension is essential for prediction the remaining cycle life of lithium-ion battery, especially when they utilize linear regression model by selecting and performance raw data into a relevant feature. The performance and interpretability of the prediction model are significantly improved. We can see figure 4 show that the discharge capacity plot reveals a stable performance in the first 100 cycle, followed by accelerated degradation as the battery near the need end of its life. To better predict long-term trend, we integrate advanced features such as voltage curve and cycle-to-cycle evolution, along with internal resistance and temperature data, enabling machine learning models to improve predict accuracy. We can see figure 5 highlights the use of Del Q 110 curve to efficiently analyze battery degradation and prediction cycle life, degradation pattern, and cycle life with higher variance indicating reduced lifespan. This statistical feature enable machine learning model to make highly accurate prediction, guiding improvements in battery design and management. This approach offers a scale framework for optimizing battery performance, enhance longevity, and supporting sustainable energy solution. In figure 6, we can see a strong inverse correlation between the variance of del Q110 and battery life cycle, making it a crucial prediction feature. Batteries with lower variance, longer lifespan, while higher variance correlation with faster degradation. By integrating additional features such as slope, intercept, and internal resistance, such data-driven approach enhance prediction accuracy, providing insight for optimized battery design and extending operational life. Here is the result analysis. Actually, we together these metrics ensure both precisions and reliability in this lifespan prediction for lithium-ion battery. We can use this two equation, error and RMSSC. We can see figure 7 shows the prediction versus actual remaining life cycle, demonstrated that the trained model performs well within the 500 to 12 or 12 cycle to the 12,000 cycle range, as the data point closely align with the diagonal line. However, between 12,000 cycle, the model prediction significantly consistently underestimating the actual life cycle. The performance gap is attributed to the distribution of the training and validation dataset, which contains cell with a total life of around 1,000 cycle. Consequently, the model lacks sufficient training on cell with higher remaining cycle life, reducing accuracy in this region. We can see table 1 present the performance metrics for the linear regression model enhanced with elastic net regularization, which predict battery life cycle. The model achieved an RMSSC, means root mean square error of 210, indicating the average prediction error concerning life cycle, and average percentage error of 9.96 illustrate the model accuracy in estimating the remaining cycle life. These metrics reflect the model's effectiveness in capturing the data underlying pattern, especially within the cycle life range of 500 to 12,000 cycle. Here is the conclusion and future work. Achieving a root mean square means RMSC of 2010 cycle and average percent error for 9.96 on dataset, demonstrating strong prediction accuracy. The model efficiently predicted remaining cycle life for batteries with lifespan ranging from 500 to 12,000 cycles. So in case its capability is real world scenario. Humans declined for longer life scale due to data imbalance, highlighting the need of diverse data set that capture the full spectrum of battery lifespan. In future work, should focus on incorporating physics-based feature to improve model accuracy and battery capture, ba- integration mechanism, expanding dataset to include diverse operating condition and exploring advanced machine learning technique will enhance model robustness and extend its real-world capacity. Thank you so much, everyone. If you have any question for zero.
Thank you, doctor. Any question? Any question, doctor? Yes, I notice the number of training set equally likely to number of validation equal likely to number of testing. You can interpret that.
I can understand once again.
Yes. Can you go to the slides of training of the experiment? Maybe number 5.
Wait. Yeah, sure.
Slide number 5. Yes, is this graph number? No. Next.
Yeah.
Number 7. Yes.
Seven.
Is this okay?
Yeah.
The training set equal validation equal testing.
Yeah.
In traditional ways, maybe validation, maybe percentage of the testing. You can divide the training set to two, 70 percentage for the training and the 30 for validation and the testing. In this
Yeah.
case, the number of training may be less than the validation test case, okay?
Yeah. Yes.
This you can interpret that.
Yeah.
Why?
Actually, describe the cell barcode life cycle and charging policy, providing valuable information about the cell overall feature in using condition. This actually is the temperature and discharge and voltage disk record for the yeast cycle. Then this measurement provide details into the battery performance throughout every charge and discharge. Like as in figure 3, show the number of battery cell for training validation and test.
Okay. Thank you, doctor. Thank you. Any
Thank you,
question?
thank you.
Okay, doctor. Thank you.
Thank you.
Uh,
Thank you.
Okay, the next one, paper number 107. 107. Ridwan Kamil, Omar Khan, Rai Sharif, Hafiz.
Yes, I'm
Hafiz Amin.
online. Should I share my screen?
Yes.
Paper 107.
You can exit, doctor.
Can you see my screen?
Yes. With your presentation, you can,
Should I start now?
no, not disappear. Where are your slides?
Can you see my screen? I'm sharing my screen now. Can you see my screen now? This is Camille, presenter for paper 107. Can you please tell Tarifuzaman Riyad to stop sharing his screen?
Sure. Yes.
Riyad,
sure.
can you stop sharing the screen?
Yeah.
Okay.
Thank you.
Can you see my
Yes,
screen
Dr.
now?
Kamil, you can share it now.
Can you see my screen now? This is Camille. I'm sharing my screen now. Can you see it? Can you see my screen?
Dr. Kamil, you are sharing it or no?
I'm sharing it. I've shared my screen.
Just give me a second only.
I've shared my screen. Can you see my screen? Because it's showing me that the participants can now see your screen.
Give me a second only.
Okay. All right. Thank you. Someone comments on the chat that they can see it online. So I don't know if you can
Yeah,
see
we can
it.
we can see your screen also. This is not his screen?
Can you see it now?
Yeah, now we can see it, Dr. Kamil. You can go ahead.
You
Okay.
can start now.
Assalamu alaikum. Thank you for the opportunity to present at the conference. My name is Kamil Ridwan, and I did this research in collaboration with Umar Khan, Resherif Zutaudeng, and Afizullah Amin at the Department of Computer Science and Engineering in Edge Hill University in North United Kingdom. So to start with the table of contents, we talk about the background and research questions, talk about the management of energy resources, the similar studies related to this our study. Then we talk about the proposed methodology, the results, the discussion of the results, and then conclusion. Then we finalize it by talking about the future work in the direction of this research. So to start with the background question, the world in general and the United Kingdom in specific is in energy transition in line with the United Nations Sustainable Development Goal 7 that shows that there should be innovations for smart city deployment of energy in line with the conference theme, which says innovation for smart city and sustainable cities. So a shift in the global use of energy resources from non-renewable resources fossil fuel to renewable energy like wind and solar is being advocated globally. So researchers have now been encouraged in the direction of how to improve the management of renewable energy resources in terms of better planning of their usage due to their intermittent nature, to encourage more utilization of the resources as an alternative to fossil fuels. So to shift from the use of renewable energy in line with Sustainable Development Goal 7 and Goal 13 that says affordability of clean energy with the use of renewable energy resources. So management of energy resources, in continuation of this presentation, for us to better manage renewable energy resources to encourage their acceptability due to their high unpredictability nature, like solar PV as a case study considered in this research, the availability is primarily based by solar intensity variation with respect to time of the day and period of the year in different locations. So the management of energy resources of photovoltaic energy system is just like an information system that helps decision making for planning towards the usage of the generation output on loads. So how efficient can we improve on this will ultimately increase the adoption and utilization of clean sources of energy, not just in small scale and large scale to replace fossil fuels energy. So to support these arguments on why we should forecast photovoltaic system output generation, a good way to enhance the EMS, the energy management system, is by conducting energy forecasting, which can now serve as an information system on the future generation output as compared with using less reliable statistical analysis method like the Kalman filtering and the ARIMA. So machine learning has been proposed as the alternative method of conducting forecasting because, one, it helps in optimal sizing of battery, which help on the long run increase the lifetimes of battery system of the renewable energy storage system. Also, accurate forecasting helps in grid stability, whereby we can actually adjust the need of the renewable energy with other resources as well, since we can have a clear idea of what their future output generation is. It also allows integration of secondary weather resources, seasonal data like humidity, temperature, precipitation, etc., which also helps in increasing the performance of the forecasting. Lastly, it helps us in detecting, we can easily forecasting can help in identifying patterns or anomalies in the system output, which can indicate when maintenance is required. This ultimately helps in reducing downtime on the system and makes them to operate at peak efficiency. So to continue on why we encourage forecasting is an hybridized system for a case study to explain my proposition. So to elaborate on the previous points and the advantages of PV energy forecasting in large scale deployment, we consider a building complex in my place of study that is serviced by an hybrid of renewable energy and the grid. So it is serviced by the grid through a transformer and a 39.02 kilowatt peak solar photovoltaic system, which is laying on the roof and also on the face. This system is being combined in an energy distribution board to the building in an hybridized form on the load. So the output of this PV system is stored in a cloud storage system online. So we got access to the data of the historical data of generation output of the PV system in order to be able to conduct artificial intelligence modeling of energy forecasting modeling to have an idea of what the future output of the PV system will be. By this idea of forecasting the future energy output to know what we can get from the PV system, we can then properly size the PV for a designated load in the building complex, or we can put the entire load requirement on the PV without the need of grid supply that is highly serviced by the fossil fuel. So to talk on the similar and existing studies in the direction of this work, previous studies have proposed time series analysis method like support vector machine that was used by Zhu et al. To conduct prediction of PV output, and also like other examples like the assembly machine learning algorithm as proposed in figure A, which they are only trying to create a multimodel of LASSO by combining MLR, LF, and SG Boost in order to increase the performance of LASSO. Also in figure B is another types of assembling machine learning algorithm whereby it combines more than one machine learning algorithm. At level 2, SVR, support vector regression, is being improved upon from the combination of assembling of SG Boost, RF, CAT Boost, and LGB. So in both cases, what they are doing is not really creating a assembling. They are only increasing on another model by the performance of other, by simply averaging the performance of other. So in a novel direction in our study, we are trying to propose a new assembling machine learning algorithm that will account for difference in how each model observe and process data. A further discussion of this will be explained in the next slide on how our own types of assembling that we are proposing will work. So for the proposed methodology, like I told you, I got access to the data of a building complex in my place of primary occupation, which is a building serviced by a 39.02 kilowatt peak. So we got the data, the building, the PV system is arranged by 28 times 185 watt PV module, as shown in this picture on the fascia. Then on the fascia, then on the roof of this building is 144 number of 235 kilowatt solar module. So this is the output. This shows the outlook of how the historical data for 5 years is generation output that I have data of. This is about 39,000 rows of time series data. This is a scatter plot showing the data output. So also we combine it with the weather data of temperature, humidity, precipitation, wind direction of this particular location, because research have shown that weather data also improves the performance of PV output modeling, unlike just using the solar radiation output. So we combine these two together to work with our proposed model of collaborative learning integration stacked ensemble algorithm that is being proposed in these studies. This model is using a stepwise refinement whereby each model sequentially corrects the residual errors from the previous one, thereby reducing error propagation and enhancing the final output prediction. The CLI stacking is built by stacking the PV output and the scale weather data as input matrix, so that the final layer will have the generation output of this in scalar output at a time t. So the data is divided into training 70% and testing data. Then we conducted a multi-step ahead forecasting. So to discuss on the results for the experimentation, using reduced studies related to this work that I have spoken about in the earlier part of the presentation, on individual models, whereby different individual models have been proposed in this study, like SG Boost has been proposed, SVR and LASSO and KNRS model. I will look for studies that pointed using machine learning model. Then we consider the assembling model, which is the meta model that I was showing earlier. So this is a residual plot over time, which shows that the SG Boost is the best because of the small variation in residual and remaining closest to zero. Also, we did the residual over frequency, which shows that KNRS neighbor is the best. All this will now be compared with our Novo model. Why we are doing this is just to create a benchmark for comparison with our proposed model in the study. So to discuss on the final result, in this study, we used 3 metrics: root mean squared error, R-squared, and mean absolute error in the final experiment, with stacking 2 representing the performance of our model, and as compared to meta-model method of assembling, which is the stacking 1 discussed earlier in the study, another individual model, which is the SG Boost KN SVR. So to discuss on the result, figure F shows that our model R-squared has an R-squared of 0.86, which is the CLI indicating the stacking 2, which performs better than the stacking 1, which is the previous literature reviewed type of stacking that has been previously proposed, which is having a 0.863, and other individual models, which showing that our model has the best. Secondly, for the other metrics we used, mean absolute error, our model had a MAE of 1.22 and an RMSE of 2.21, which is also the best when compared to other models like the stacking one, which is based on creation of meta model, which achieved an RMSE of 2.45 and MAE of 1.47. On the general goal of this, we created a table to show all the results, showing that our stacking 2 model achieved the best in terms of MAE, RMSE, and R-square as compared to all other models that were benchmarked based on previous existing studies in the direction of this work. Generally, this shows that all other models show greater tendency for large errors in long-term photovoltaic output forecasting as compared to our own model. This will be justified on the plot on the actual and predicted on the 30% test data in the next slide. So for the conclusion, we plotted the actual and the predicted for the real on the test data, which aligns in the 2022 point of the data, which shows that our stacking 2 model CLI has a better output of predicting forecasting on the test data horizon as compared to the other model, which is the meta model, the previously proposed method of assembling another individual model. And also, this is the best that for performance of smart grid stability and will help ultimately to in management of renewable energy resources, which also helps the adoption more for long scale PV deployment as an alternative to fossil fuel resources. So the future direction of this work is we want to conduct the real-time inferencing, whereby we'll be able to compare the online and offline accuracy. Because what we have now is the online accuracy. If we deploy it in real time, then we have an idea of what's the offline and compare the generalization of the model. And also we want to conduct transfer learning to be able to assess the CLI model that we are proposing versatility on a different photovoltaic system domain, because in this case now it can work well on the data set that and the system that we have in my school, but the major aim is for it to be able to work on any PV system when the model is deployed. So now we want to conduct transfer learning to assess the performance of the model on a different PV system. Thank you for listening.
Thank you, Doctor. Thank you, Dr. Kamel. Can you ask question? Do you have question? Okay, thank you. Good presentation. Thank you, Doctor.
Thank you.
Okay, thanks.
Because they will hear you.
Okay, so it's okay. Okay.
Yes, agree.
Doctors, you can hear the doctor here or no?
Are you okay? Can you hear me?
Dr. Kamil.
I can hear you.
Yeah, you can hear us, right?
Yes.
Okay.
Online audience, can you hear me?
Yes, we can hear you online.
Okay, thanks. Yes. Now, paper number 111. Okay, object
Okay.
identification using active acoustic sensing.
Okay, thank you very
Okay.
much.
Thank you, doctor.
Thank you very much. Hello, everyone. My name is Mr. Matsumoto from the University of Electro Communications in Japan. And today I'd like to talk about object identification using active acoustic sensing. And this study is mainly done by Mr. Yamazaki, but he's my student, but he graduated a few years ago. So I would like to introduce his research instead of him. At first, I would like to introduce the motivation of this study. Cameras and optical sensors are commonly used as methods for object identification. However, there are many applications using vision systems such as face recognition, object detection, activity recognition. However, of course, the camera and optical sensor uses the light, so it is difficult to accurately identify objects using these methods in environments with insufficient light or in situations where certain materials reflect and or absorb light. On the other hand, object identification methods using signals other than visual light, such as ultrasounds and infrared light, are also being researched. Similar applications can be founded, such as face recognition, object detection, and activity recognition, like the vision system. However, infrared rays and ultrasonic waves can identify the shapes of an object, however, but cannot identify its material. For example, a fan considered unknown object, we cannot know whether it is made by the plastic or stones or other and so on. So we focus on the techniques of active acoustic sensing. Active acoustic sensing is a technology that identifies that characteristic of an object by actively emitting sound to the object and measuring the reflected sound. And there are some applications of active acoustic sensing, such as activity recognition and gesture recognition. And in this study, we aim to incorporate active acoustic sensing into robots so that they can identify materials even in environment with insufficient light. And this is the application scenario. So we supposed to set the speaker and the microphone to each arm of the robot. And active acoustic sensing is performed by applying a robot arm to a target object. And this is the mathematical formulation of the proposed method. And let us define GC as the impulse response of the material correspond to the position C. And C include the position of the microphone and the position of the speaker. And CM represent the microphone position, and CS represent the speaker position. And under this condition formulation, the situation can be seen the middle figure. The input signal is S, and it's transferred to the Z to the Y. And Y can be represented by using the convolution, and when we apply the signal to the okay. Can you see? Yeah, and like that. So this is the convolution style in the time domain, and when we apply the Fourier transformation, we can convert to the signal into the frequency domain, and in the frequency domain, we can obtain this kind of equation. And to measure the transfer function, a switch signal with constant frequency increase from 100 Hz to the 10,000 Hz was used. And this is the outline of the experimental equipment. We use a smartphone for send the sweep signal, and the speakers play the sweep signal like that. And this is the target material, and this is a microphone to record the sweep signal. And we also record the sound from the microphone by using the PC. And for the first experiment, we used asymmetric materials. In this case, we used the three substances with high symmetry. It's a ball type of material, and it's the same size and the same shape. We used the polyoxymethylene and urethane and polypropylene, as shown in these figures. And we first acquire the training data from the three angles, vertical, horizontal, and the depths, based on mark placed on the object. And after that, the direction of the matter is defined as shown in the following figure. And this is the obtained waveform and the spectrum. So as shown in this picture, the waveform is similar, and the spectrum is also similar for the polyoxymethylene. And other material, we could similar result like that. And this is recognition result. The recognition result using SVM is 87%, and the recognition result using light GBM is 100%. And the result of the principal component analysis shown in this figure, and as shown in this figure, the same material is layouted in the similar region, like that. And for the experiment 2, we conducting an object identification experiment using 6 substances with low symmetry and in size and shape, like that. In this case, we used the common stone, for example, basalt, andesite, or some other materials. And we also obtained the training data at various points on two-dimensional plane, as shown in figure. And the direction of the matter is defined as shown in the following figure: horizontal and vertical, and one side of the stone is flat. So we set the flat on the ground, and we put the speaker and the microphone at the various point to get the training data. And this is a waveform of each stones. So as shown in this waveform. There are sometimes they are similar, but sometimes they are different. So we could obtain, of course, the result is bad, but some effective recognition result could be obtained, showing this result. So I would like to conclude my presentation. For highly symmetrical object, the feature hardly change with an angle, and it was found that object can be identified even from audio data at unknown angle with a small amount of training data. On the other hand, for the less symmetrical object, the feature changes a lot of depending on the position of the microphone and speakers. So it was found that the identification is difficult without increasing the amount of training data. But we think that we have some possibility to identify such kind of unknown object by using our approach. Okay. Thank you very much for your listening.
Thanks, Doctor. Any question, online audience? Do you have any questions? Okay. Doctor, why you need to detect the material of the object?
Because, for example, I think the supposed scenario, we would like to develop a robot to explore the unknown place. For example, the cave or some catch. Yeah. Yeah. For example, the robot. Yeah. The robot is in the unknown place. Yes. For example, pick up the stones and kind of materials is made. If it's, for example, it's the application scenario is to apply our method to the exploring robot. For example, it's difficult to explore. It's difficult for the human to explore such kind of unknown places. For example, I am not sure whether, for example, the deep sea or the moon or some other unknown place, I suppose. And in such kind of case, it is important to measure the material, to identify the material. Yeah. So such kind of
We exhibit the weight of the object.
Weight. In this case, we do not consider the weight, but of course, we can apply the.
After to need to detect the material, you can detect, you can expect the weight of the object be by dimensions or.
Yeah. Of course, it's also important. So, it's perhaps we also can measure the weight or some size of the material by using other sensors. Robot hand.
In the effector. In the effector of the robot.
Foot of Foot. What do you mean?
In the effector.
Yeah. Hold. Yeah. Hold is if necessary.
Thank you, Doctor. Next. Thank you. Next paper, 112.
112, Prof. Elia, Prof. Do you hear my voice, Prof? Hello, Prof.
Hello, Doctor.
Yes, do you hear my voice?
Number 111, 112.
112?
Yes, Elia?
Yes, I'm Elia, Prof.
Yes, thank
Do you see my screen?
You can yes, you can start now.
Okay.
Okay,
Wait,
yes,
okay.
I can see your presentation.
Okay, thank you, Prof. Khalid. Yes, Assalamualaikum warahmatullahi wabarakatuh. Yes,
Alaikum assalam wa rahmatullahi wa barakatuh.
okay.
Can you start now?
Good afternoon, Prof. Khalid and all of the audience here in this room. Thank you for the time to us to present our study. This is a big opportunity to us to present our study in this seminar. Let me introduce myself first, Prof. My name is Elia Christine Ingrum. I am from University of Indonesia and also from National Research and Innovation Agency for Indonesia. So our study here is entitled Sustainable Approach to Energy Management, Multi-Sectoral Collaboration for Second Life Electric Vehicle Batteries. This is the outline of my presentation. The first is introduction, and then next the method and result discussion, and also the last presentation is about conclusion. The introduction of the study, we all know that electric vehicle, including battery electric and also plug-in hybrids, play a key role in the shift to clean energy by reducing reliance on fossil fuel and lowering greenhouse gas emission. By replacing internal combustion engine vehicle, EV hopefully help mitigate climate change and then to improve air quality also and indirect reduce respiratory and also cardiovascular disease. EV also improve energy efficiency, particularly when combined with renewable energy sources, which further contributes to the preservation of the environment. But we also know in the implementation, there are many challenges faced by many countries, including Indonesia. We know that the batteries are the most expensive component of electric vehicles, influenced by material costs, production scale, R&D, and also market dynamics. And the previous research showed that the manufacturers...
Dr. Elia,
Yes.
please, slow.
Yes.
Please, slow, yes. Slow, please, step by step.
Too fast, yeah, Prof, yeah, too
Yes,
fast, yeah,
yes,
sorry.
Very fast.
Yes. Yeah. Okay, pretty
Too fast.
fast. Okay.
Yes.
Yes.
Slow.
Yes, this is the
Thank you.
challenge in EV battery cost and production. The previous research showed that the manufacturer focus on efficiency improvements and economies of scale in the EV battery production. The target is to reach $100 per kilowatt hours. It is will make the EV more competitive with the traditional vehicles. And we also know about the product, all of the product have their own life cycle. It is also the battery. In the first life cycle, EV battery lasts 5 to 15 years and it losing 20 until 30% capacity, but it's still retaining 70 until 18% usable energy. It means that the usable energy enables to reuse in the stationary energy storage, for example, in order to reducing environmental issues from battery disposal. And related to the market and the challenge, the EV second life market, the second life battery market also has a strong economic potential. However, the challenges include identifying key ecosystem actors and overcoming organizational and cognitive barrier in circular economy adoption is also the big challenge to in many countries. In the other view, we also have to consider about important aspect and considerations regarding the utilization of second life battery and renewable energy storage system. There are six aspects that we define from the literature. The first is about energy storage, and then the economic sustainability, reliability, performance metric, grid support, and also the planning. This is the aspect that we have to consider if we want to apply the second life EV battery. And this is the methodology that we use in this research. The study identify the main actors, their roles and also challenges in the second life electric vehicle battery ecosystem. And to achieve the goal, we use literature analysis to identify the main activities, actor, and challenges. And we use the Scopus database with several keywords in the title, abstract, and keyword to find publication related to this topic. We also apply document filtering based on language, year, and also open access article. In the second filter, we only use the article that accordance with the research topic for further analysis. And we also use the framework from the other researchers for the life cycle, the battery second life cycle, the battery life cycle. The first life of the battery begins with production and distribution, where the raw materials are processed to manufacture battery, which are then assembled into electric vehicle and distributed to use to the customer. During its first life, the battery powers the EV until its performance declines. When it reaches the end of life, it is collected and dismantled for evaluation, determining whether it can be repurposed or maybe refurbished or maybe recycled to minimize waste and maximize resource efficiency. And come to the second level of the battery. After the collection, the battery undergoes testing and refurbishment, where its condition is assessed to determine if it can be repaired or maybe extended use. If suitable, then the battery enters into its second life through reuse and repurposing, where it is utilized in applications, for example, in energy storage system or pick up power solution and the other stationary uses. And the final stage of the life cycle, the battery that can no longer be reused are sent to recycling and also disposal. Valuable materials such as lithium and then nickel and then the cobalt are recovered to be used in the new battery production in order to reducing the need of the raw material. This is the result of our research. We already identified the key actors, role, and challenges in second life battery life cycle. For the battery production stage, the actor face the challenge related to supply chain dependence, high production costs, industrial capacity, and also the government investment favorable policies. For the assembly in vehicle, they face some challenge. Integration of second life battery, and then design limitation and collaboration complexity among our partners. And for the collector and also collecting and dismantling stage, the actor, we identify 4 actors here: the logistician, car dealer, EV OEM, and also testing authorities. The challenge related to traceability in the battery and the standardization procedure, and also coordination and the cost. And the cost is the big challenge, and the need standardization and regulatory compliance. For the testing also, we identify 3 actors here: the battery second use expert, the researcher, chemical industry, and technician, but they still face the infrastructure apparatus and also the technology for test the second life battery, and the standardization challenge is the big challenge that they face. And for the refurbisher, the second refurbisher, the refurbished stage, the actor we define 4 actor here: the refurbisher and manufacturer, the battery life cycle management, battery second use joint venture, and also recycles. The design complexities, the challenge are the design complexity, establishing reuse standard, disassembly and high recycling cost also as a challenge. For the distribution stage, we have 3 actors: logistician, EV charging infrastructure provider, and also commercial properties. And the challenge are the high logistic cost and compatibility with existing infrastructure, and limited understanding of economic benefit. For the reuse and repurpose states, the actor is only the energy storage provider. They still afraid with the curious with the safety risk from the second life battery, and also the regulatory and installation difficulties also the big challenge and difficulties predicting battery lifespan. And for the return battery states, the actor relating to the public transportation firm, for example, and also energy companies or grid awareness, they face the limited consumer awareness and the traceability and standardization challenges. And the final states, the actors battery manufacturer and battery second use joint venture. The challenge is the fluctuation in material quality and quantity. And for Indonesia itself, we also face some challenges here. The first is related to economic challenges in Indonesia. The high initial purchase price make EV less accessible to budget conscious consumers, and also the maintenance cost it is also the economic challenge in Indonesia. And the last is declining price of new battery, because the declining price of new battery creates uncertainty for the second life battery market. And also we identify the technical challenges in Indonesia. For example, the limited charging infrastructure, battery range anxiety, and second life battery degradation. And consumer perception issue, also the big challenge in Indonesia. We know that the consumer lack awareness of second life battery benefits, and the used battery are perceived as lower quality and less safe. And the last, the complexity of battery repurposing discourage adoption. And we propose the solution and policy recommendation, develop educational program to improve consumer awareness is needed to make easier the adoption of second life battery in Indonesia, and implement incentive and regulation to promote second life battery use, and establish centralized digital infrastructure for battery tracking and reuse. This is the conclusion of our study. We found the key activities for second life battery, the collection, testing, refurbishment, and deployment of second life battery in secondary applications such as energy storage. And the key actors are EV manufacturers, recycling firms, energy providers, and third-party organizations handling used battery. And the main challenges is unclear regulations, safety standards, limited infrastructure, and uncertainty in battery lifespan and performance. For the success strategies, we propose that cross-sector collaboration is very needed to elaborate these challenges. Regulatory support and economic incentive also needed. Investment in monitoring technology and the development of standardized safety and efficiency protocols. For the future research direction, feasibility business model is very interesting to research, and enhance collaboration strategy, and the establishment of comprehensive technical and regulatory standard for second life battery application. Thank you, Prof. Khalid, and everybody in this room. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Alaikum assalam. Shukran. Thank you, Dr. Elia. Any question, online audience? Any questions?
Thank you, the presenter. I'm Maruf Kolaole from Nigeria. I really appreciate the presentation. However, I want to ask that the research work, what are the problems you are trying to actually solve? Then what are your objectives? Then can you match your objectives with your conclusion?
Dr. Elia,
Yes.
can hear Dr. Maruf?
Can
Yes.
you repeat, Dr. Maruf?
All right, thank
Please.
you very much. I said, can
Sorry,
you
yes.
Tell us the problem you are trying to solve with your research, and what are the objectives of that your research, and can you match your conclusion with your objectives?
Yes, Dr. Maruf, as I tell in the presentation that my research is the goal is to find the key actors and also their role and the challenges that they face when they adopt the second life EV battery. You know that EV batteries, if they have passed the first life in automotive in EV cars, for example, they still have the much energy, 70 until 18% usable energy to use maybe for the other energy storage, Dr. Maruf. So we want to know who are the actors and what are the rule and what the challenges that they are faced if when they adopt or use the second life EV battery. And our conclusion, we already define in Indonesia some actors and also what they rule and the challenges that they face in Indonesia. Thank you.
All right, so I can see that you identify poor quality materials during the point of your discussions as one of the challenges of second EV battery. So I don't know, because I'm a material research scientist, I want to know what are the specific problems with those materials that you have identified during the course of your research.
Yes. Yes, Dr. Maruf, thank you for the question. So the specific problems in Indonesia, for example, focus in Indonesia, Dr. Maruf, that we face that the EV batteries is the hazardous waste. Yes, Dr. Maruf, yeah, hazardous waste. So the handling of the EV batteries waste is very important to be regulated by the government. But we identify in some country or maybe in Indonesia, let's say, there are some informal what we've said. Informal workshop, yeah, informal workshop that they dismantling without permission to the government.
Okay.
So we want to elaborate the ecosystem, how the government can elaborate the ecosystem that informal workshop can also fit with the regulation that settle in Indonesia.
All right, thank you very much.
Thank you, Dr. Maruf.
Any question, doctors? Thank you, Dr. Maruf. Shukran, Dr. Thank you, Dr. Elia. Okay.
Yes, thank you, Prof. Khalid. Thank you.
Okay, that's all for this session. Okay, thank you for all. Assalamu alaikum.
Waalaikumsalam.